talk? Nobody? Well, that's good and bad. It's good because that means this is all new. Bad because it means you didn't see it. But at least you're here, so let's look on the bright side. And I think that even if you had seen it, actually, this is tons of new material in this talk. For those of you that weren't in the previous session, this is just a bio slide. My role on Windows Azure is I'm architect of a component called the Fabric Controller. The Fabric Controller is something you're going to be learning about as we go through this talk. And as the architect, I help define where the fabric's going, the Fabric Controller is going, the kernel of the cloud operating system, what features we're going to put in place. And I work lots with other teams around Windows Azure and across the company as well, kind of the connection of the Fabric team to the outside world at a high technical level. So I work with guys in identity and access like John Chuchuk, you might have heard of, and other people, Anders Vinberg, and other people that are technical fellows at Microsoft in other groups. This is we only got 60 minutes, so I've packed this thing. So I'm going to be moving pretty quickly through this so that I can show you everything that I want to show you. I'm going to start by showing you a little bit about Windows Azure cloud architecture, the data center architecture. Then I'm going to take you behind the scenes of what happens when you deploy a service to Windows Azure. I'm assuming everybody in here has deployed a service or knows what I'm talking about when I talk about deploying a service to Windows Azure. I'm going to talk about how we maintain the health of the system and show you some demos to highlight some concepts. And then I'm going to show you pull the curtain back and show you a little bit about how we develop and operate Windows Azure. So first, starting with data center architecture, this is a sketch of the Windows Azure data center architecture. If you've got your own data center on premises, your data center probably looks a lot like this. The differences between this and what you might have is that this is very homogeneous. We've got very little variation in terms of hardware up at the switch and the router level, at the load balancer level, the aggregator level. We've got very little variation down here at the bottom. Of course, we're going to get more variation over time, but variation and heterogeneity is actually the enemy of efficiency and simplicity of management. So we want to keep things as homogeneous as possible. It also lets us buy in bulk, which is kind of nice because we like to save money. Now this is actually a picture of one of our data centers. This is an older data center, standard racks with servers in them. And we've got these new data centers that are coming online, which we've got videos posted on the web that show you a little bit about what these new data centers look like. And this is there's no sound to this, so I'm just going to be showing. This is a Quincy, Washington data center that just went online earlier this year. And the goals of this architecture is that it makes it really easy to put these things together and to scale the data center easily. So we've got these containers, the packets, where we take these containers and put them in data centers that have very thin walls in key strategic areas for the climate, so that both the ambient heat and coldness can help drive down the cooling and heating costs on the data center. You can see this is an IT pack. We've got the HVAC pack, and we put them together, the mixing evaporator and the IT pack, which is where the blades are, and then they're completed. So that's a quick look at where Microsoft's data centers are going. But inside, still, from a logical perspective, you see what you saw in the previous slide. What we do from a software management perspective is we divide the data center into groups of racks that we together called a cluster. A cluster is roughly 1,000 racks, or sorry, 1,000 servers, typically around the neighborhood of 20 racks. And this is variable and can change over time, but right now that's kind of our unit of fault isolation. So there's something called a Fabric Controller that runs in a cluster and manages the servers in that cluster. If there's something catastrophic happens to the Fabric Controller, then that's the unit of failure, is the cluster. Although we've got tons of reliability and availability built into the Fabric Controller, so we shouldn't ever have anything catastrophic happen. The Fabric Controller is responsible for provisioning the hardware, for managing the blades, and for the management of the life cycle of applications. So I'm on the Fabric team, of course. We define how we manage and monitor the health and provision software, including the host operating system, hypervisor, virtual machines onto these blades or servers, and how we deploy Windows Azure services onto these, Windows Azure applications. So part of my role is helping to define the service model, the application model for Windows Azure going forward, because the Fabric controller is the main entry point for that service model, definitely the compute and network aspects of it. The Fabric controller in a lot of senses is the parallel to the Windows kernel or kernel on a desktop or server operating system, because it is managing the hardware resources and virtualizing them. We provide a view to you so that you don't even see the details. You don't know how many machines we have. You just see a pool that is effectively looks to you as infinite. Hopefully we've got enough capacity to meet your needs. And what happens underneath to get that capacity is something that you don't worry about. Same thing as in Windows, where you get virtual memory. Your app doesn't really worry about how much RAM is there unless it's really concerned about performance, because the virtual memory manager in Windows virtualizes that resource and shares it across apps. Same thing with processors. We also manage the lifecycle, like I said. So the Fabric, it deploys an application to the cluster, monitors the health of the application, is responsible for things like updating the application. And there's two inputs to the Fabric controller. When we set up a data center, we've got this big file called Data Center XML, which I'll show you a snippet of Data Center XML. This is what Data Center XML, this is basically what we feed into the Fabric. Now, this Data Center.xml has descriptions of the IP addresses that are assigned to each cluster, the IP addresses of the blades, the IP addresses of the load balancers, the aggregators. All of the hardware in the data center is described in this giant file. And the clusters are described in here, like here's a cluster name. So the Fabric, when it's deployed for a particular cluster, goes and looks at its region of this and then knows where its hardware resources are. So we build a new cluster out by adding to that datacenter.xml, and then after we provision the hardware, we put all the settings in that datacenter.xml and then bring up and bootstrap the Fabric controller. Here's what the Fabric controller wants to eventually have a cartoon about it for. This cartoon actually to be about the Fabric controller. So people say when I tell them I'm working on the Fabric controller, they say, hey, you're building CloudNet, or Skynet, sorry. You're building Skynet. And they say it like it's a negative thing. Now, the way that we bootstrap a Fabric controller is we've got something called the utility Fabric controller. It turns out that the Fabric controller itself is a Windows Azure service. There's another instance of it, the Fabric controller, kind of the parent root instance, that knows how to start up other Fabric controllers. So when we do provision a cluster, this utility Fabric controller knows how to start up this new Fabric instance, another Windows Azure service. The utility Fabric controller, because it's not doing anything other than bootstrapping Fabric controllers and serves in updating the Fabric controllers, it's really not important to the operation of the data center. So there's only one of those for lots of clusters. And this is the USC, like I said, feeds this Fabric controller that's a pool of hardware resources to manage. If you look inside a cluster, this would be what we would see is, again, the network topology at the top. We've got top-of-rack routers on each rack. And then we've got blades or servers, or we call them nodes internally, on the racks. And these nodes are standard servers. I can't tell you exactly how big they are just because that's a secret. The only thing I will tell you is that our VM sizes range from 1/4 of a core and 750 meg of memory up to an extra large, which is 8 cores and 14 gig of memory. Not that that has anything to do with actually how big those servers are. So don't try to extrapolate anything from that. And that's actually subject to change anyway. The Fabric controller is a multi-instance Windows Azure service. Like we talk about creating a highly available Windows Azure service, you want multiple instances of your roles. The Fabric controller has multiple instances. I will show you the Fabric controller service definition in a few moments. There's typically 5 or 7 instances of the Fabric controller, so we can tolerate multiple failures across racks or nodes. The Fabric controller reserves the top blades in each rack for things like the Fabric controller itself and some other core infrastructure services. And if there's a a failure of one of the Fabric controller replicas or the primary. If it's the primary, we'll fail over to a replica, and that will take over. If a replica will service heal, fix up, the Fabric controller knows how to fix up itself as well in that case. And we support the rolling upgrade concept, just like your own services would in Windows Azure. When we're deploying the Fabric controller, about once every 2 months, we do a rollout of a new Fabric controller across all of Microsoft's data centers. Of course, this is invisible to anybody running Windows Azure services just because we're doing this kind of update on the fly, just like Windows Azure services support. When the Fabric controller gets this new hardware, it starts it up. It needs to get it up and into the pool of resources that it can deploy Windows Azure services to. So the first thing that happens is at the bottom of each of those racks, there was a power distribution unit. And there's an IP address of that power distribution unit so that we can talk to it and control the power to individual blades or certain nodes on that rack. So what we'll do is power on, Fabric controller powers on the blade when it comes into this resource pool. And the blades are programmed to PXE boot. So they'll PXE boot from the Fabric controller. The Fabric controller has a PXE server in it, something called the maintenance OS, which is just Windows PE. Windows PE starts up. It's got its own code in it, which connects with the Fabric controller, or actually formats the hard disk and then pulls down through Windows deployment services the host operating system and hypervisor from the Fabric. The Fabric controller also has Windows deployment server built into it, which is then broadcasting images to these various blades that need them. So we bring down the Windows Azure operating system, which is brought down in a VHD. Everything is boot from VHD and VHD oriented in Windows Azure. In fact, Windows Azure had boot from VHD before Windows did. It's one of those kinds of concepts that went from Azure back into Windows Server in Windows 7. The system reboots into that VHD. Now we've got the Windows Azure operating system up. We've got the Windows Azure hypervisor, and something starts as part of that image called the Fabric controller agent. This is also called the host agent. You'll also see it called the RD agent. RD stands for Red Dog. Anybody know what Red Dog, where that name came from? I'm sure somebody's heard the story by now. Nobody? You want me to tell you? All right. So Red Dog, the Windows Azure team had a code name for Windows Azure before it got the name Windows Azure, and that was Red Dog. And apparently it got its name. Nobody will confirm this for sure, but the myth or the story going around the Windows Azure team is that Dave Cutler and some other people who originally started Windows Azure were driving in northern San Francisco and passed some place on the side of the road, big sign up in front called the Pink Poodle. And then they said, that's a cool name, but we can't call it the Pink Poodle, so let's call it Red Dog. And so that's how it got its name. And I haven't actually gone, as far as anybody knows, and looked for the Pink Poodle, but so I can't tell you what kind of establishment that would be. So actually, once the host agent comes up, it makes a connection to the Fabric controller, and it's now ready to take commands. What I'm going to do now is go into a machine that I've got up in this. I'm TS'd into CorpNet, and I've got a cluster that I'm showing you here with a tool called the Fabric Viewer. This is a diagnostic tool we've got that will show us what's going on inside of a cluster. This cluster that I'm looking at its name is CO2 app stage, or stage app 02. This is a staging cluster that we've got in the cloud. We've got several of these staging clusters. These are where we deploy services, part of our release cycle that I'll be talking about later. So just to be clear, I'm not looking at data from a live production cluster. I'm looking at a staging cluster. There's all sorts of compliance and auditing and special access codes that you require to actually get access to data from production clusters because of the privacy and whatever else. So this, to be clear, this is a staging cluster that doesn't have any customer services on it. And what I'm going to do is connect to that. I've got a connection to that with a tool that we call the Fabric front end. And we've got a tool called, it's a Fabric controller client, which connects to the Fabric controller front end. One of the roles inside the Fabric controller is called the front end, and it accepts commands from typically other components in Azure that I'll talk about, but also we've got this operational tool where we can talk directly to the Fabric controller. So I can issue commands like get nodes, and this might have to re-authenticate. I might have to do this twice because the connection timed out. Oh, there we go. So this is a list of the blades inside of that cluster, and you can see that what we have here is our blade IDs and then blade IP addresses, and then the state of that blade. And back in this picture, let's see if that picture is several hours old, so I don't know if this represents that. Oh yeah, here we go. We've got one of the blades in a state called human investigate, which means that this blade has encountered some hardware problem and has been pulled out of rotation. And if we go into the Fabric viewer, we should be able to see it. It's right there. These green represent services or service instances. Multiple services consist of an instance, and we're going to come back to that in a second. So that's a quick view of the Fabric's inventory told to us by the Fabric itself. Let's move into deploying a service now and talk about the steps that happen there. Most of the time when you deploy a service, you're probably using the portal or you're using some management tool that goes and talks to the service management API and deploys your service. So the workflow goes like this at a high level. The service this definition and configuration are uploaded through either the portal service or Concero, which is now called System Center App Manager, which manages multiple clouds, on-premises SCVMM clouds, as well as Windows Azure. The portal provides one for developers. The package is passed to something called the Red Dog front end, which is the primary interface to Windows Azure. The Red Dog front end sends the service to a Fabric controller in the appropriate region. I'll talk a little bit more about the placement algorithm in a second for how it figures out which cluster to send it to. And then the Fabric controller stores that in its image repository and deploys the service. What we're going to do the next few slides is go into a level deeper on what happens here, starting with RDFE. RDFE is a Windows Azure service as well. In fact, we can find RDFE inside that staging cluster. There's a staging version of RDFE in there by calling get tenants. And actually, there's RDFE. So we're seeing all of the services running in here. This is RDFE CO2 Stage 2. It's the Red Dog front end for the staging environment. And Red Dog front end for the staging environment is actually visible here too. I think it's one of these things, and it's huge. This is it, yeah. So when I clicked on this instance, you can see that the Fabric viewer told us what tenant it is. That's RDFE O2 stage, and it also highlighted in yellow all of the other instances of that service. So you can see RDFE has a bunch of instances of varying sizes across a whole bunch of different blades. The way that, so RDFE, besides being the place where you deploy your services to, also serves as the central point for subscription management in Windows Azure, for billing in Windows Azure, for user access. So this is the place where you configure live IDs and also multiple co-admins. All those concepts are provided to you by RDFE. Well, as we saw in the previous slide, it's also responsible for picking the cluster that a service goes to. And the algorithm it uses to pick a cluster, first it looks at the data center region. You can specify, of course, when you deploy your service that you want it to go to a particular data center region, like Southwest US or anywhere US, and then the RDFE will pick it for you. You can also instead pick an affinity group. So you could say assign a service to affinity group. What that will mean is that will force RDFE to try to deploy that service to the same cluster as any other services you've got in that same affinity group, so that those services now are they're close to each other. They're close to each other, you know for sure, in the network topology, because it's a multi-tier network architecture across the clusters. If you're in the same cluster, you know you're talking to each other, basically going across racks. And so you've got that network proximity. But if it's got a choice between clusters, then it uses this weighting algorithm to figure out the load on the clusters, looks across the clusters, says I can deploy to any of these N clusters. What's the load like? And the way that it measures load is based on two resources. One is the virtual IP addresses. So each cluster is assigned a pool of virtual IP addresses to assign to services. And the second is the number of VMs, or the cores, available. So it will then look based on those two in this algorithm. Would you like to see the algorithm? It's kind of secret, but I'll show it to you. And I hope I'm not giving too much away. Here's the algorithm. This is the actual algorithm. So it's like aggregated resource usage, where resource usage is H across clusters G of the capacity of those resources across the clusters, weighted across all of the clusters. Then it goes into this, chooses the min across those of the resources available, and then deploys to that. So that's the algorithm, roughly. We call it a weighted coin toss, is the algorithm, is what the algorithm is called. It's very sophisticated. So it turns out that when you deploy your CSDEF to Windows Azure, there's a couple of translations that happen to your service definition. The CSDEF that we provide to you, expose to you, we make as simple as possible. Very straightforward, just exposing the things that you need to worry about or be able to access the features that we've published. And if you've ever, how many people have looked at a CSDEF? Just probably anybody here that's used Windows Azure seen a CSDEF. It's just some simple XML. So I'm not going to spend any time showing you that. There's actually two schemas for CSDEF. There's one that we provide in this part of the SDK. It's the published features. And then there's one we've got internally that's accessible only to some of our internal services, where we can roll out features early to internal customers before we make them public. So this is a way for us to make sure that we've got it right without screwing up in public. Once we make sure we got it right, then we push it out into the public CSDEF schema so that you can have access to it, and we also make sure Visual Studio understands it and so on. Some of the things that we allow in the internal schema, access to more update domains. So there's 20 update domain limit now. There used to be 5 update domain count limit. Now we've upped it to 20 just in the last week or so. There's also a limit on the number of fault domains you can have, and that's 2. And you can actually override that at all with the public schema. With the internal schema, you can specify more than 2 fault domains. This is, of course, necessary for anybody that's writing a stateful service on Windows Azure. A stateful service where they're actually storing data on the local blade on the disk, because the model, if you were in the previous session for Azure, is stateless. You should assume that the blades can fail and you lose everything there. But you've got to be able to write stateful services somehow. There's got to be something that's stateful to have durable storage. SQL Azure and Windows Azure Storage, for example, are stateful services. They are storing stuff on the local blades. They run on Windows Azure. So they're not really fitting into the application model, but they choose not to because they know how to replicate their data across their blades. But they need more than 2 fault domains. They're replicating data 3 times. If they have a failure while they're in the middle of updating, for example, so one of their update domains goes down, they've got 3 instances, let's say. One of their update domains goes down, and then their other 2 instances on a separate fault domain fail. That fault domain fails because the top of rack router, which is the single point of failure right now, fails. Then SQL Azure is screwed. It's offline. So those guys create more than 3 fault domains. In fact, they sometimes create 5 or more fault domains so they can tolerate multiple failures and failures while they're in the middle of an update as well. And that's exposed to them through this. Now, there's some services that are, then when that CSDEF is translated to the core internal version of the service definition called the WAS model, the Windows Azure service model. That one is internal only, and it's actually something we're migrating away from. So this is one of the cases where the original Windows Azure team developed this, and they said, well, this is a really complex model. Let's have a simplified model for customers so they don't have to worry about this weird syntax and all this junk that they don't care about. And so your CSDEF comes in, it's converted to a WAS model. We still have some internal infrastructure services that are written to the WAS model that we're going to be changing over time to use the CSDEF model. One of those is the storage service. So I've got the WAS model for the storage service here. The WAS model's got some features that haven't even showed up in CSDEF yet. So one of those is the ability to co-locate roles. So here's one of, let me zoom it. So here's one of the containers inside of Xstore's service definition, this WAS model. And you can see it's a native container. And that means don't put it in a VM, put it on raw hardware. So the Fabric controller knows how to manage raw hardware as well, put services on those. And you can see that it's got two roles in it. So this container, which is a VM or a blade, whoops, has two roles. Has, whoops, this one. Wait, why am I having a caps lock? That's just, I'm having trouble with my zoom it here for some reason. Ah, here we go. Looks like my caps lock key. Well, okay. Here we go. One more try. Here's the extent node role, and here's the partition server role. So these are the two of the roles inside of Windows Azure Storage, and because they're part of the same container here, they are co-located. This is a feature that we've heard customers say they would like, is the ability to co-locate two Windows Azure roles inside the same VM. And this is something that the Windows Azure Fabric Controller knows how to do, obviously. We will eventually make that available to you in CSDEF as well. So that's an example there. And I mentioned that the Fabric Controller also has its own service model. This, oh, actually I don't have it in this directory. Let's go to, I call this the PDC just because it fits into my directory structure, by the way. It is build, just in case you were confused and forgot on your way in and from seeing the 500 signs that are outside the door. But here's the Fabric Controller's own service definition, and you can see that it's got two roles in it, basically. The Fabric front end, FFE, which we were just talking to, and the Fabric Controller itself. We also call the combination of these two, by the way, the Fabricator, because it fabricates things. So there's a look at the Fabric's own model that UFC deploys. But actually, that's not the end of the service definition story. The Fabric Controller internally converts it into its own internal format. So it takes the WAS file, or it actually, the Fabric Controller itself, expects something called an SVD, the service something. I think Laura has forgotten what SVD stands for, but that's the really, really internal Azure Fabric Controller service model. So this is what it uses to describe things, and I'll show you an example of that a little bit later. In the service deployment steps now, once you get to the Fabric Controller with this SVD file, the Fabric Controller processes the models, determines the resource requirements for your service, and creates role images. Those images that you provided as part of your CS pack for your roles, it then takes and creates images that then it's going to deploy to blades to get those VMs up and running with your role code in it. And so part of it obviously is talking to a host agent, saying, here, host agent, here's an image. To put this in your image repository, each Fabric Controller instance, or each host node has its own image repository. The Fabric Controller itself has its own image repository. And actually, we can see the images in the Fabric Controller itself by typing a command called list images. Whoops. Is it get images? Images. Unfortunately, the commands get image list. The command syntax for this is a little bit rough since it's evolved over the last 4 or 5 years. These are all the images inside of the Fabric's image repository. You can see it goes on and on and on. So these are on those Fabric Controller blades. We're going to look at the image repository in an individual node in a little bit, but you can see zip files, which are the agent runtime files, the guest agents in there. You can see CSXs. This is your service configuration or role configuration. It comes down as this. You can see CSDEFs are stored in there. And you can see the TRDs and SVDs here, which are the internal Windows Azure Fabric Controller service model. And then there's VMs up here, way up here. There you can see VHDs for these different roles that have been stored in the repository as well. And the OSs are up here as well. So that's an image repository. And once it has placed those role images on the node and put them in this repository, it creates virtual machines. We call a virtual machine a container, as you probably saw from that WAS file container. Once we start the virtual machine with the role as a VHD, the guest agent starts talking to the host agent. Also, at the same time, while we're doing that, we are configuring network resources to wire up all your instances of your service. connecting them to the load balancer, assigning them IP addresses, setting up packet filters on the VMs so that your instances can only talk to your instances and nobody else's stuff. Now, one of the things that their Fabric controller's got to do is figure out where to put your instances. So you might have, say, a service with 2 front ends and 2 middle tiers. So you've got 2 instances of each, and they're across 2 fault domains and 2 update domains. So it's got some choices in front of it. A fault domain being a rack, it's got to figure out which fault domains do I want to put these different instances. Some of the constraints around placement are hard constraints, like you say you want an extra large VM. Well, we need to find a node that has 8 cores on it available to give you your extra large VM. And by the way, we do not over-provision cores or memory. So when you ask for an extra large VM, you get 8 cores and you get 14 gig of RAM. You're not sharing that with anybody. Disk, you might be sharing with somebody. And I'll talk about that in a second. But then, besides the hard constraints of fault domains and this resource requirements, we also have soft constraints that we want to do placements to optimize the way that we do upgrades of the data center. And I'll show you that in a little bit. Now, once we figured out the constraints, well, then we follow the steps that I basically talked about on the previous slide. Here's an example of deploying a service. And this is where the front end here has 3 instances. You can see a count of 3 update domains. It might just, because I haven't specified fault domains, it's getting the public 2 fault domains. But the Fabric controller will actually try to spread it across more than 2 fault domains. In this case, it spread it across 3 fault domains. A large VM is 4 cores. These blades right here have 8 cores on them. So it found 3 nodes that have the appropriate number of cores, required number of cores across those 3 fault domains. For the back-end role, it found 2 blades that meet the requirement of these mediums, which is 2 cores. Happens that the nodes with the front ends had enough room for the back-end runs. And so the Fabric controller will try to co-locate your roles on the same blade if they fit. And that is obviously good for several reasons. It's good for the network traffic in general in the data center, and it's good for communication between your roles if they're talking to each other directly. And then the load balancer is configured and wired up and then connected with your containers, your VMs. And life starts up for your role instances. You can see, for example, I've got in this staging deployment, if those of you that were in the previous talk, I've got my branding police. That branding police that I showed you is actually running here in staging. Here's its tenant ID or its service ID. In Fabric controller, I can enter that as a filter, and what gets highlighted in green are the instances of that service. So this is branding police. It's got 2 front ends and 2 back ends, and you can see there's 4 instances. They're extra small VMs, so they're actually sharing cores. And you can see that I've got 1 on this blade, 1 on this blade, and 2 on this blades. That tells us what about these 2 instances? What has to be true for the fault domains to be honored about those 2? Where's my cursor? Oh, here it is. What has to be true about these right here? Can they be both web roles, front ends? Can they be both front ends? Can they be both back ends? No. One's a front end and one's a back end. They happen to be co-located. So this is a place where it co-located. And to prove to you that this is branding police, I can click on this VIP and say, where does that take me? To branding police's front end. This other VIP, by the way, is the RDP VIP 3389, because I've configured this thing so that I can RDP into it as well as somebody publishing my service. And I can do get LB tenant settings, for example, get tenant LB settings, and put in that service ID that I copied from up here into the FC client. And actually, I need to get rid of those spaces. And my cursor, I'm having trouble seeing. Here we go. And so what this is going to do is show me how the load balancer is configured. And I'm going to see the load balancer with 2 endpoints, the 3389 and the port 80, programmed to point at my instances. So you can see I've got 4 instances. These are the IP addresses of those containers. You can see here's the public IP address, viewable from the external world, port 80, and the load balancers map them to two of internal endpoints. There's two front ends, web role instance 1 and web role instance 0. Then you can see port 3389 on the same VIP, that port mapped to port 20,000, which is what we use for the remote access forwarder inside of Windows Azure when you configure it for remote desktop on the worker roles coming through from. So the way that this gets plumbed is through the front ends. So there you go on load balance, how the load balancer is programmed. One of the things that this is just trivia, but the way that we assign instances, so when you look at your role in the portal or through the service management APIs, you see instance 0, in_0, in_1. The algorithm we use to map those to fault domains and update domains, we actually have to march through fault domains and update domains to do this assignment, to do this placement, mapping of an instance to those various concepts. And the way that we do that is fault domains are the primary index and update domains are secondary index. So the way that we round robin across them, so here's instance 0 would be in fault domain 0. And that's the way we fill it in. Basically, we're just have a pointer into fault domains that we're incrementing for each instance we add, and then a pointer into update domains we're also incrementing as well once we round robin. So this actually is, there's APIs, of course, that you can get back the instance ID, but this is invariant. This is actually, baked into the Wint fabric is this mapping of instance IDs to fabric, to fault domain, update domain counts or numbers. Once you deploy a node, you're going to have a bunch of VMs on it. And this is what it looks like. It's a standard kind of Hyper-V image, except you've got a couple of components here. You've got the image repository, which has the OSVHDs, the zip files you saw that were deployed from the fabric down to that node. You also have the fabric controller host agent, which is sitting there as the emissary from the fabric. The trust boundary is that hypervisor boundary. Now, the host is trusted, the host agent is trusted to a point in the security model of Windows Azure. Obviously, if somebody punctures the virtual machine boundary, which means we've got a problem in Hyper-V in general, which is a huge, huge problem, and we've taken, obviously Hyper-V's gone through even formal analysis to try to make sure that we don't have any security vulnerabilities in the Hyper-V boundary. But if somebody were to puncture it and compromise the host agent, then that blade is kind of isolated as well. From a security threat perspective, we've designed the system so that a compromised blade can't go and infect other blades. And a compromised blade can't go and infect the fabric controller either. It's trusted from the perspective that the fabric controller will send it stuff and expect it to be uncompromised and talking back to it. So if it's malicious, it gets access to the other VMs on there. But other than that, and whatever else the fabric controller tells it, it has access to that. But it limits the scope of damage, and hopefully that's never going to happen. If we take a look at an empty blade over here in the fabric viewer, if we go to our list of nodes, let's find an empty one and take a look at the node internals. And wow, we got a lot of. Did I do get nodes on it? I thought I did. Where is it? Oh, I guess it's scrolled off. Let's try it again. Get nodes. And then we're going to take a look at a node, one of those nodes in the staging cluster that doesn't have any services on it, using the fabric controller front end. And so here's one right here. The ones that have RD, those are instances. So this get node internals on this node is getting oops, I meant to, sorry about that. What I meant to do was not show copy the IP address. So this is now going to show us what's inside of that node. And what we're going to see is the state of the node, some information about the state of the node, the IP address of the node, and the list of images in that node. And we're going to see the disk configuration of that node. We're going to see the volume configuration of that node, which are all things that the fabric controller has to know. So if I scroll back up here, you can see here's the information about the node status, the agent version, the current OS image and hypervisor image, the images that are stored on here, which are the images for any roles that might have happened to have run on there, as well as the guest agent in here, the diagnostic agent, which I'll talk about later, is also on here. And then you can see this thing actually has 8 cores. It's got 16 gig of memory, just coincidentally, and it's got 4 disks. And it's got one virtual disk on here, which is the boot from VHD disk for the hypervisor operating system, the host operating system, and then it's got volumes also mounted on those disks. That's a look inside of a node from the Fabric controller's perspective. When you deploy a role instance, there's several things that happen. There's the number of VHDs that are created. The host OS image is a VHD, and the way that we share that across instances is to create differencing disks on top. Each VM gets its own differencing disk on top, so if you can scribble all over your OS, you're not affecting anybody but yourself. You also have a role VHD created for you. So we create this role VHD, stick your role code inside there. And you could have multiple instances of your role on the same blade. We share that base image VHD by putting differencing disks on top of that as well. So if one of your VMs scribbles all over your role volume, it's affecting only that instance, not another instance from that role on the same server. And for the resource VHD, that's just a dynamic VHD that we create. That's that one, that resource VHD. You can stick whatever kind of cached stuff you want to in there. And so you end up with a certain level of drive letter configuration, C, D, and E or F. The role VHD it's mounted as volume E or F, depending on whether you did an update on or not. Because when we go through an update, we leave the current VHD attached for your current role code. We create a new VHD for your new role code. We attach that. Then we shut down your role, detach the VHD, and obviously this is going to have a different drive letter. So if the role code was at D or E, then it is F, and then the next time you update, it'll go back. And the OS is on D, the resource volume is on C. And we can actually TS in. Well, here's just a picture of the relationship between those things. The resource disk being dynamic, the others being differencing VHDs on top of the image base. And what I'm going to do is TS in and just show you really quickly those concepts inside of Branding Police. So I'm using the Remote Access Agent plugin that we've configured for my service. And once I'm in there, I'm going to show you Disk Manager, which will just solidify what I just described about the volumes and the disks, and show you a little bit around what's going on inside of those disks, and also the processes that are running inside of your VM. And I actually have 15 minutes left, don't I? So I'm going to be speaking even faster. So get ready. Because I think how far am I through the talk? Halfway. That's good. Yeah. Plenty of time. All right, so here I am in the VM, and if I run Disk Manager and run, of course, Task Manager, then we can see some stuff. And one is those volumes that I talked about. Here's the role volume. If I open that, here's my role code. It's sitting here in app root. Here's Process Explorer itself. Here's the bin directory with my role DLLs right there, webrole.dll. Here's the OS volume, and here's the resource disk. And this disk is also, or the volume on top of VHD. This is also used I clicked on the wrong one. This is also used for writing crash dump file. If you actually crash your VM, like blue screen it, your dump file will go in there. The paging file is also there. So that's taking away some disk space too. And if we did a DIRS, looked at the hidden files, you'd see your paging file there. That's a quick look inside of a VM. Now, as far as deployment performance, this is not confidential, obviously, what the performance is like, because you all see it all the time. What I'm showing you here is a breakdown of the 50th to 75th percentile of deployment performance, which is approximately 8 minutes. is what we're seeing. Actually, this is a couple months old, so it's actually improved a little bit since then. Your mileage is going to vary, of course. And one of the things that we're working hard on, which I'll show you in the next few slides, is improving the performance of this whole staging pipeline. This is actually starting at RDFE and going all the way down to your roll coming up and being ready and talking to the outside world, about a total of 8 minutes. This black chunk in here is Windows booting. And for the first time, Windows, when we boot, well, just like if you deploy Windows on premise, it's a generalized image. Right? So the first boot's going to be a specialized boot, and that's always more expensive. There's about 300 meg of data written to the OS differencing VHD during the specialized boot of Server 2008, which is what we've got running here as or R2, which is what we've got running in the cloud for you. We've got improvements work on all of them. We are shooting for under 5 minutes for everybody's deployment. Not just the 75th percentile, but going out past that by the end of the year. And we're shooting for 2-minute updates. So we've got some pretty aggressive goals. I'm going to talk here for a second about how we're going to achieve those. One is to improve the performance by reducing the contention on disks. Now, one of the things about cloud is that it is a shared resource. You are sharing network and other things with other tenants, what we call them, as you've seen, in the cloud. And when you deploy your instances to a VM, today we've got a certain number of disks that we then stripe using Windows striping, and then put the VHDs on those stripes. So you can see that on the left, the striping. We've got one big volume spanning those disks, and the VHDs go down on there. This has two implications. One is that I/O from one tenant writing to VHD1 is going to affect the disk performance of VHD of the guy accessing VHD2 if they're accessing at the same time. The second is, if you get a failure of one of these disks, you've just lost the whole volume, and you've lost all the VMs on that blade. Disks, as I'll show you, are the #1 most flaky resource in the data center. So disks are going bad all the time. What we want to do is make it so that if a single disk goes bad, not everybody's affected. We limit the damage. So we're going to start moving in the next couple months the clusters to use JBOD configurations of disks. Just separate disks with separate volumes on the disks, and we will put the VHDs on the individual volumes. If the VHD spans we're too big for a volume, we'll span it at the file level across the volumes. And that way, in this same case here, if that same disk goes bad, it's affected only the VM for VHD2, which is bad, of course, but hasn't affected VM1. And in the future, we'll probably make it so that you can with new server technology in the data centers, we can be able to come and replace the disk that's gone bad. That's probably way further down the road, but we're working on that. But the other benefit you get here is that VM1 can be going crazy on its disk and VM2 at the same time, and they're not affecting each other. That improves the performance of boot and improves the performance at runtime as well. And then we're also doing this. That shouldn't have animated like that. That's a copy and paste problem. But another problem another performance improvement we're going to make is that today, this differencing VHD on top of the OS is dynamically grown. And so if you've got multiple VMs booting at the same time, which happens when a blade first boots, you're going to see fragmentation of the VHDs, this differencing VHDs. You're going to see disk seeks as the file gets extended, and extending a file in Windows is a relatively expensive operation. So we're moving to pre-allocation, where we're going to pre-allocate the differencing VHD. We're going to pre-allocate the resource dynamic VHD so that all of the files are their maximum size, and there's no extension at runtime. Because we're not over-provisioning the space on the blades, we can do this. The other benefit the other thing we're doing is also prefetching. So we're monitoring the boot of the OS because we're in control of the OS. We've got the same OS across the data centers. We monitor in the lab the boot of the OS, and then we write the data, pre-populate the differencing VHD with the data that's going to be written, or read, sorry, so that pre-allocated differencing VHD already has data from the base in it, so that when the OS goes and tries to modify something, it doesn't need to go back and do a read from the base VHD. The combination of these two things is going to have a dramatic improvement on that big black bar that you saw in that previous diagram. Actually, I need to do this from inside of the cloud, or instead of remote. Let me grab the name. I was razzed in before so I could actually do this, but now I need to do it from my VM in the cloud, so let me grab the name. Azure boot U. Oh, I'm actually going to be able to get into it. Okay, so what I'm going to do, this is an unoptimized boot. This is basically what you see today. I'm going to start this VM. And you can see the runtime up here, the uptime. Here will show you, this is the sysprep boot, about how long it'll take. Fortunately, I'm going to burn some time here. So I might go just a few minutes over. I apologize for that, but I think that this is worth stopping for. We're at 21 seconds. So this is going to come out to that black bar. If you looked at that black bar, it was a little over 2 minutes. So that's about what we're shooting for right here. Which is actually, for even a sysprep boot, it's actually pretty good of Windows Server. We're at 50 seconds. And you know what, at this point, I'm not going to wait the other minute. I'm going to show you the optimized boot now. Let's go look at the optimized boot, because the difference is already going to be visibly dramatic using these algorithms. Okay, so let's start this one off. Now note the uptime. This is the exact same image, just with the pre-allocation and pre-fetching that I've talked about. We're at 13 seconds. The other one, by the way, is already finished by now. It's about 2 minutes. And boom. So it's under 30 seconds at this point, and we still have some more improvements that we can do to bring that down even further. And the second boot, let's see the second boot, which is the one that's going to happen when we service the OS underneath you, for example, or you recycle your role for some reason, you reboot it. This one is worth showing you because it's just really, really fast. The shutdown is actually longer. Here we go. On. Now watch the uptime. So it's about 10 seconds. So that's some of the stuff that's coming. Now, updating the host operating system, that's something we do about once a month. We march through update domains. We never take down 2 instances across different update domains. And what that means is that we've got a prop placement issue. If we fragment update domains, we put update domains from different services on the same blade, we can end up where we've got to basically march through all 1,000 or so machines in a cluster sequentially to update the host OS, because we have to honor your update domains. So this is an example of 2 allocations. I'm going to throw this up and let you do the graph theory problem here. But the second allocation, the one on the bottom, is one where we can only update one of those instances because we've got update domains from different update domains from 2 different services on the same blade. On the top one, we only have the same update domains, update domain 1. So that means we can take down 2 blades at a time. One update domain 1's blades, update domain 2's blades. So the algorithm is actually pretty simple. We will try to keep only one update domain, roll instances of one update domain on a blade, even if they're from different services. We'll try to do that, and that helps us get into a placement that optimizes the updates. Now, the update still takes us hours and hours and hours because there's lots of services that have more, internal services especially, that have more than 5 update domains. Some of our services have 20 update domains or more. And so those guys, we've got to march through all 20 sequentially, whatever blades they're on, one by one by one. And we also run into the fragmentation problem. So we can run into cases where it takes us over 12 hours to update a data center with a new host OS because we're honoring this thing. update domains. Finally, let's talk about health. And part of the Fabric Controller's job is monitoring the health of data center resources as well as your services. This chart right here shows you kind of quick and dirty what we do when we detect certain problems. So if we detect, for example, that the guest agent has crashed or the VM has crashed, we will recycle that container. We will blow away the OS, differencing VHD, and start fresh with a new OS because we're afraid that something's been corrupted there. It could be in a bad state, and so we will try to reset it. If we detect a hardware issue, the host agent informs the Fabric Controller. The Fabric Controller then takes that node out of rotation by doing something called service healing, where service healing I'll describe on the next slide. But here's a breakdown of what we're seeing in the data center as far as hardware issues. So you can see that disk is, and this is on a relatively new cluster. Older clusters, the disk failure rates are about 80% of the failures are because of disk. Here you can see it's 40 to 50%. As time goes on, we generally see these numbers go up as the disks age. Same thing Google sees in their data centers, and they published a lot of data on this as well. Memory errors are another problem. So the way that we're detecting disk failures is we've got Smart enabled on these disks, and so Smart errors are surfaced up through the Fabric Controller and will initiate service healing operations for a graceful shutdown of that blade. The same thing for memory. We detect memory errors on the boot of a blade if the queried memory capacity of the server mismatches what we think it should be. We know that we've got a DIMM problem, and actually that's the majority of the memory problems we see are DIMM issues, where the DIMM just loses connectivity with the motherboard, or it just fails, and we've got a memory problem then. And then other stuff as more random networking failures of the hardware, other hardware, motherboard, and things on the servers. When we move gracefully, we will shut down the services, the instances that are running on that blade, start them up on another machine. We also, so we don't have rogue blades, ones where your instances could be running there, and we start up the instances on another machine, that would be a bad thing for us and you. So what we do, if we've got a server that we can't shut down gracefully, we will go to the power distribution unit and just basically yank the power on it so it goes off, and then start up the instances. Service healing looks like this. Blade HIs, like you saw, and we then migrate the nodes, the instances to another blade, and rewire things appropriately. Now I've got about 2 minutes left. I'm going to go a few minutes over just to give you a quick look at Windows Azure operations and development. So we've got lots of different teams in Windows Azure. Just in the core infrastructure itself, we've got lots of different services implemented by different teams. Some teams have multiple services they're creating. And all of these, we don't want to be in lockstep with each other, like, oh, you have to release at the same time we do, and let's all get together and plan our releases. We like to be loosely coupled, so each team can go on its own cadence, adding features as they need to add them, adding bug fixes as they need to add them. The Fabric Controller is one of the services that goes at its own cadence. And when we are releasing an update, well, first we test in our own boxes. We've got something in the Fabric called the Fabric Simulator, which I'll show you really quickly. The Fabric Simulator I've got running in this other. Actually, I need to close this. All right. Branding Police VM. The Fabric Simulator I've got running over here. And the simulator looks like this. And so I've just got a lightly populated simulator. And I actually can, here's a Fabric viewer look at my own simulator running on my own desktop. This is Fabric's virtual cluster. You can see it's a lot smaller than a real cluster. These machines only have 4 cores in them. I've manually gone in, and I've manually HI'd or human investigated these nodes to cause a service movement. And I can do that at any point in time by setting the state of the node. So I can do set node, force node state. Let's get the get tenant containers of Mark's demo, which is my little sample service. And I've got, you can see that these 3 correspond to these right here. of my little sample service. So I'm going to blow away that node. Here's the node ID by doing that force node state to human investigate. This is telling the fabric that node is bad. And what I will do now is come over and do another snapshot of the cluster. This is the same kind of snapshot that we do every several hours for diagnostics that we were looking at in staging. And then what I can do after this snapshot's done is go add that snapshot to the fabric viewer so that we can look at what happened graphically. So here, let me go to add local snapshots. Here's the new local snapshot, util. Which one's the newest one? It's this one. And there we go. The guys moved from that node, which I just HI'd, down to this node, all three of them. So again, the co-locations at work for those guys. This is a front end with 3 different instances across different fault domains and then 2 other single instance roles, so those get all co-located, like I told you. Now, when we do a release cycle, they go through 3 stages: integration, stage, and production. Integration is just like we throw it in just to run some heavy stresses on it and make sure this thing is actually not stupid and stupid broken. Once it passes those, we move it into staging. This is where we meet with other services in staging, which is a more like we're baked and we think we're pretty good. It's just a final test before we go into production. Once we clear that, we go into production. Each stage usually takes a few days to a few weeks, depending on what's going on and what kind of the size of the features we're releasing. Here's actually from a few days ago, the release. Every day, the release lab sends out an email to all interested parties saying, here's what's going on with in-stage and prod for the core infrastructure services. This is just some of them. I've trimmed this. But you can see that certain dates, certain releases are going into others are going into production, others are going into staging. So everybody knows what's going on and slips their features in appropriately. Here's the Windows Azure Ops guy. That's what we're trying to make the Windows Azure Ops guy, actually. But here's actually the Windows Azure Ops room. This is the Operations Center for Azure worldwide. You can see that it's not one guy, and they still look bored, though. Actually, that might have been posed, I don't know. But there's like 5 or 6 guys in there. And that's monitoring Azure worldwide. There's a backup Operations Center as well. But that's all it takes. And you can see they've got heads-up displays to look at what's going on. Now, the information that they're looking at comes from monitoring. This monitoring service, where you saw the monitoring agent inside the node, that is constantly spitting out data to Windows Azure tables, monitoring tables. All of the components in Windows Azure are doing this all the time. So core infrastructure services spit out to Windows Azure monitoring tables, and we've got Windows Azure monitoring service, which is a big service. You might have noticed it in the listing of tenants I had in staging, because one was there. And that is constantly looking at the tables, looking at the new stuff coming into the tables and running rules on them. If I see this entry in a table, that means that, oops, there's something went wrong, and there's workflows associated with them. One workflow can be, well, some of the things we do with that is just generate kind of analyses in other portals. Like this is a trend analysis for RDFE deployment operation performance. This one is spot trends and anomalies in, for example, the fabric. This is the fabrics logs, looking at the number of threads on a fabric controller instance over time. And then we can look at API availability. So we're also monitoring the success or failure in the MDS logs of API requests against the fabric. And we also have something else called the canary in the cluster. Well, I call it the canary in the cluster. So that each cluster has an canary instance, so a fake, basically dummy, just monitoring, kind of health checking instance of a canary service, an extra small on each rack. And all that thing does is the canary instances all just try to talk to each other in all the different ways they can. That's all they're doing all the time. Can I talk to the guy in the next rack? Can I talk to the guy in the next rack? Can I talk to the guy in that other rack? Can I talk to the guy in the next cluster? Can I talk to Microsoft.com? Can I talk to the guy over in this other data center? They just do that all the time. They're just chatty. Just basically, it's like Twitter in the cloud. And here's the canary heads-up display. You might have seen this on one of the monitors in the ops room. Those reds are, we were doing some maintenance on some of the canaries. So that's why those are reds. They're normally not red. So this will show us if there's problems with network connectivity or between anything and anything else, or if there's a problem actually with the blades they're on. So we get an idea, it's kind of a sampling of what uptime looks like for customer services, because here's a customer service that we've got just constantly deployed everywhere, being busy all the time. And then some of the workflows actually fire off alarms. This is actually a picture of an alarm that was picked up by the guys in the operations room. MDS saw the Fabric controller spit out the fact that one of the Fabric controller instances had crashed. This is a mini dump file alarm. Now the live ops guys look at it and they say, well, and then they look at the health of the Fabric controller. What happened here is it automatically failed over. Another instance picked up and it healed itself. So they didn't call the live site. We've got DevOps guys. Each developer takes turns monitoring, being the backup for the live site guys. This particular incident didn't generate a live site call to the devs because it's like, okay, so there was a crash. It's automatically filed as a TFS incident so that the devs see it. They can go investigate on their own leisure, but it's not affecting the live site operations, so no need to call somebody up. But you can see that's the actual schedule from a few days ago that was published. Every week we publish the schedule of who's on call. These are actual developers in the Fabric controller team for the Fabric on call. So if the live site guys have a problem that they don't know how to resolve, this is who they call. Don't call them, by the way. I told them not to talk to you. So that brings me to the end of the talk. I'm sorry I went over. In fact, there was more I wish I could have shared with you, but these 60-minute sessions are a little bit cramping. Normally sessions are 75 minutes, and really that would have been a much more comfortable span of time to fit this into. But I hope you found this interesting. How many people found this interesting? Let's see, raise your hands. Okay, good. How many people were bored? Well, those people probably already left anyway. So I hope this gave you a cool inside look of what's going on in Windows Azure, gave you some confidence in what we're doing, that we actually are running things with some kind of deliberate science and operational rigor, and gives you confidence in deploying to Windows Azure. So with that, please send me an email if you've got any questions, and please fill out an evaluation, and I hope you enjoy the rest of build and deploy successfully and have great success running your services on Windows Azure.